Okay, settle down, guys. Let's get started. Happy Halloween. An old student of mine basically put up these pumpkins yesterday night in Boston. He carved AI. You can't scare people more than anything else, right? So not surprisingly, I'm wearing my AI t-shirt because that's the best way to scare people, especially you, because that just works. Okay, so what we, and then there is, for the people who are coming late, there is some candy going around. If your sugar levels are dropping, have you so today is going to be sort of we will try to wrap up the discussion about multi-layer neural networks, parts of which have been called deep learning. But as you saw from last class, you can't understand neural networks without understanding fundamentals of machine learning. Okay, otherwise you basically only have some sort of idiot's guide or whatever, the dummy's guide to neural networks. So again, today too, we will actually have that sort of a discussion regarding a variety of things that you can do with respect to machine learning, machine learners, regularization, covariate shift, etc., and how that is connected to neural networks. And then, in fact, one particular form of biasing neural networks turns out to be convolutional nets that we will also discuss. Okay. What happened? Okay, that's fine. You can pour the candy like somewhere in the front or something in case people are running out of energy, they can do it. Okay. So last class in the extended session, we looked at this stuff, basically about the fact that in particular, there are really two kinds of learning regimes that you can think about. One is sort of the traditional learning tasks. These are characterized by sort of a few mostly manually extracted or hand-coded features, okay? And then basically in this regime, this sort of comes from the classical statistics and also the early machine learning, most of machine learning too, not just early. Where basically you are considering, you have to consider the number of parameters that you're trying to learn is not too high. Typically people try to learn hundreds of parameters. Okay, there are like two different aspects going on here. One is the dimensionality, the other is the number of parameters. Okay, the dimensionality is how many input features are there. The parameters is how many weights, in the case of neural networks, how many weights does the neural network have. Typically they are connected, but they are really different aspects. Okay, this regime typically tended to go with low dimensional data, not data, really low dimensional learning tasks where you could actually have high dimensional data, but then that's been converted into a set of features that somebody extracted because they know how the world works. Like for example, grading you guys is a high dimensional task, but we converted it into a low dimensional learning problem, which is basically the vector of your scores in your homeworks, projects, etc. Okay, and once I do that, then I can consider how many parameters I want to use to learn the distribution of your grades. Okay, in the training data I will give somebody previous year's grades, let's say, and in the test I'm trying to predict the grades given the same vector. So this is low dimensional data. Typically you can call them under-parameterized networks, not too many parameters. So in some sense you add parameters as needed, because of which it's like if you're given a bunch of points, you try to first look for straight lines, which is basically going to get in 2 dimensions only requires 2 parameters, ax plus b. Then you look for parabolas, then you look for cubics, etc., etc. So this is how you go typically. This is what much of machine learning basically went that way. And then the other side is high dimensional tasks where of course the input itself is high dimensional and nobody is extracting tasks for you from the data. So you just have to deal with the data in the raw form. Do you see what I'm saying? And in those cases, that basically happens, for example, speech, images, signal processing, etc. Interestingly, in speech, image, signal processing, etc., much of the area called speech processing, much of the area called image processing, etc., they tried to extract hand-coded features from images, hand-coded features from speech signals. Do you see what I'm saying? So that you can reduce the signal into a low-dimensional input. Unfortunately, what happened was these tasks are speech, image, etc. These are classic tacit knowledge tasks. Remember from the beginning of the semester? So really nobody really knows how we see the world. So they sort of try to make some sense of it, saying maybe we'll be looking for edges, maybe we are looking for textures, maybe we are looking for pitch in the sound, etc., etc. So these are the features that they would try to extract. But there are many other scenarios where we do have pretty reasonable theories, and so getting the hand-coded features would be easier in those scenarios. Okay. In the case of speech and images, etc., as I said, for a while those were being used as low-dimensional learning tasks with hand-coded features. So in fact, when I was doing my undergraduate study, way before you and your parents were born, I was doing speech recognition, isolated word speech recognition. And those would essentially be using some specific features that signal processing people have figured out as useful, like in my case I use what's called capstone coefficients. Okay? What has been happening now is, in fact, you could essentially say, I don't know how to learn them, or I don't have any idea what to make of this data, so let the learning strategy learn the features also. When that happens, you don't know what features were learned. It's just you can only see whether the final task is sort of good or bad. I mean, the performance on the final task is good or bad. This has been known as sort of end-to-end speech recognition, end-to-end image processing, etc. Even at the start of, just before like AlexNet sorts of times in 2013, before that too, people would still be using a pre-processing step, get hand-coded features out of their images or speech recognition systems, then apply learning. This other one, essentially, you have very high dimensional data, and you just let the learner figure out the features. The reason that wasn't being done before is because nobody thought that would scale. And two of the reasons it actually wound up scaling partly is because A, we have a lot more data from which to train learners, way more data. You can't understand, being young guys right now, you don't understand that people used to have only a few photographs. People only take a picture like on the special occasions, for example, maybe for a wedding or something. Here you take a picture for almost every waking minute of your life, sometimes seconds of your life. And then what do? You put them upstairs, you put them on the web. So they're all available as data to be trained, to train the systems. We'll talk about this, for example, the fact that the entire area of image processing used to have this one picture, more or less. If you read an image processing paper, you would see this woman called Lena, who was a model from Sweden, and they basically cut off her picture such that it's only the face and it's sort of PG, at least PG-13, and then basically use that to do everything, such as edge detection, whatever. Any theory of image processing was done on that. Now, the academic benchmark called ImageNet has 14 million images. And the kinds of things that Facebook and Google, etc., use to actually train their systems have billions of images. And where are they getting them from? You have a Facebook account, right? How many of you have a Facebook account? You're giving it to them. And you're surprised, how come Mark Zuckerberg knows where I am? Well, you told him so, okay? Anyway, so that's useful to know. So that's the data increase as well as, of course, the compute part, which is, as I said, the GPU aspect wound up helping quite a bit in terms of speeding up the gradient descent epochs speed. Okay? If you understand that, and so in these scenarios, typically, we call these typically the over-parameterized scenarios because nobody starts with, let's say, look for a line or something. Okay? They essentially give way more parameters than there is data. Okay? So first of all, just make sure that you understand that we're talking about three different things. Number of data samples, that's one. Dimensionality of data, that's the second one. Number of parameters, that's the third one. These are all different, and you need to be able to understand which is which, and in what way are, given a problem, do you have lots of data samples? You can have lots of data samples with low dimensional data. You can have high dimensional data with very few data samples. You can do either of them with fewer versus larger number of parameters. When you wind up having number of parameters that's much larger than the amount of data you have, in classical statistics, that's a dumb idea. Because it's basically like saying I have 5 points. Can you go ahead and fit a 250th degree polynomial to it? You have 2 points, you already have a line. Do you see what I mean? 5 points will get you up to 4th order polynomial. And you're trying to fit a 250th order polynomial to the data. So in this, basically, you try to go up in the expressiveness, thinking in terms of bias versus variance trade-offs, in terms of how is the training error falling, and whether or not we should increase the capacity of the learner. Capacity meaning, for example, increase the degree of the polynomial. Here you just say, to heck with it, we'll start with huge number of parameters so that nobody can complain. And then see what happens. And a few things happen. You don't really know that things are working sort of, and do they actually make any sense? And that's where we spent time talking about it in the extended session last time. In particular, essentially, if you continue training after the error on the training data becomes 0. And by the way, some of you were actually awake enough to ask at the end of the extended session last time as to if the training error becomes 0, how are you changing the weights? Well, it turns out that we will talk about it today, that the loss function that you minimize for learners is not just the error. It's error, plus what we'll talk about as regularization term, plus whatever the heck you feel like adding. And in fact, there is an entire cottage industry of loss function engineering. Okay, you want this stuff, it's not working well, do you want to change something? Okay, I'll add one more factor to the loss function. Because loss function is the objective function for your optimizer. Do you see what I'm saying? So you compute the error with respect to that. Okay, and in fact what happens as we'll see when we talk about regularization today, is what is happening in this part is the training error has become 0, but the regularization factor continues to change. In particular, we'll see that regularization is connected to kind of keeping the weights smaller. And the reason that is needed, we'll talk about in a minute, but in general, if you have very high weights, and you have, let's say, you have 13 billion parameters, let's say, okay, and you need to you're trying to train yourself on 1 million data points. 1 million data points, but 13 billion parameters. Do you see what I'm saying? You can make each of these parameters stand for one of these data points. This is what's called in neurology, neuroscience, they talk about these grandmother cells. Like, is there like a cell just that recognizes your grandmother and nothing else? You see what I'm saying? And so similarly, you can have a neural network where each particular parameter or a very small subset of parameters are just training themselves on one particular data point. If they do that, they will do a good job in reducing the training data. But they will be compressing. They won't be learning anything. Remember, this compression versus generalization is a classic trade-off in machine learning. Okay? To stop weights from specializing so much, stop parameters from specializing so much, you need to say nobody gets to have very high weight. You see what I'm saying? So that essentially means you take the weight vector and put some restrictions on the size of the weight vector. The magnitude of the weight vector. Remember, the number of weights would be, of course, the amount of data, the number of features. But the magnitude can be minimized. For example, if you take a L2 norm, the Euclidean norm, then you're saying W1 square plus W2 square, etc., the whole square root of that needs to be minimized. If you take L1 norm, you are basically saying the magnitude of the absolute values of the weights added up should be minimized. These kinds of regularization terms are used to essentially avoid overfitting. Overfitting is another way of saying I'm just remembering the data. I'm not learning anything about the future. Okay? So that's what is happening here. So basically, as you go forward, you see that the additional parameters allow for a smoother interpolation in terms of the smoothness is measured in the norm of the vector. In particular, there are so many features that different sets of features might be used slowly to figure out which ones will actually fit the training data best while reducing the weight vector size. This is what was happening. And then we also pointed out that when this happens, there are all sorts of interesting issues, such as adversarial examples that can be generated. We talked about our ostriches and so on. I also realized that as of this morning, 21 people have watched the recorded video. So that basically means I think more than 70 people left. When I said, look at the extended video later on, but there are only 21 people. Even by pigeonholing arguments, a whole bunch of people have not watched. They were just hoping that they will get things through, but let's see what happens. Okay, so one other thing that I want to mention is this distinction that I'm teaching you is not well understood by the overwhelming majority of people who think they understand machine learning. Not talking about Jeff Hinton, okay? But Jeff Hinton is not the only machine learning specialist. Everybody, your friends, friends, their dogs, their cat, they're all machine learning specialists now. And most of them don't understand this distinction. So much so that, in fact, the companies use it. People misuse it. They say, I'm doing deep learning. I told you earlier on that people can say they're doing deep learning with one layer, okay, and one unit. It's really deep, except, remove other things. You would think that that's like a silly thing, but let me show you this. I don't know how many of you have looked at this. About 2 years back, Google, basically, there was this huge amounts of articles like this. Google uses DeepMind AI to cut data center energy bills. To put this in context, DeepMind doesn't do anything useful for Google. Okay? DeepMind basically figures out how to solve one more video game. Like yesterday, there was a Nature paper about StarCraft. The number of people who depend on that result, 0. So DeepMind has major revenue profit problems. They're always at the edge of being thrown out of Google. Like if you keep track of what's going on, like every once in a while they'll say, Google people are figuring, hey, what are these guys doing? It's true they're in UK, they don't get paid as much, so they're cheap, but really what are they doing? They're doing good science, but they're not making anything for the bottom line. So every once in a while, if they actually do anything that is at all possibly sellable, they'll make a huge deal about it. So one time somebody basically said, this was this thing, Google uses DeepMind AI to cut data center energy. Now of course Google says, we sneezed, New York Times will write it in the front page. Google sneezed today, right? So this is what they did. This is deep learning, of course, and all that stuff, and it looks like a great idea. Read this and tell me which regime is this in. It has 5 layers, 5 hidden layers, 50 units per layer. Okay? And then it has these hand-selected features. This is stuff that's not done by Larry and Sergey. This is done by people who work in air conditioning and building cooling. They have decided these features make a difference in figuring out whether or not buildings can be cooled. Do you see what I'm saying? This is hand-selected features. How many are there? It's a high-dimensional learning problem with 19 dimensions. If you can't tell the difference between this and, basically going from raw data, raw image data, then you are just part of the masses of people who think they understand the distinctions and the trade-offs. And I hope you won't be one of them. I'll definitely test these things and will feel very sad at the end of the final exam, but right now I'm in a good mood. Okay, so keep that in mind. So again, as I said, the biggest successes for the high-dimensional regime came in the tacit knowledge areas. There was no other theory. The so-called human-extracted features basically fell by the wayside because all the great human-extracted features for vision and speech, etc., you could do much better than them from learned features. Okay? Okay, a few things that we want to get to, basically we sort of lead us to the convolutional networks. One is that there's a bunch of pre-processing steps that you have to do for any big network before you start actually doing the gradient descent. Okay, some of which we want to just walk through. They're kind of important. Each of them can be like, actual lecture in a if I have a deep learning course, but I'm not going to do that. First thing, of course, is you want to start by scaling the inputs. If the inputs basically have very high variance in terms of the magnitudes, okay, what you want to do is you sort of normalize them. It's like, how many of you have heard of z-score? Right? What is a z-score? You can actually compute your z-score, for example, for midterm. You can take your score minus the mean, for some of you that will be negative, divided by the standard deviation. That's the z-score. Okay? If you do the z-score, then in essence, any data basically is being converted into zero mean unit variance. Do you see what I'm saying? Okay? That's one very simple thing that we would do, and it sort of also winds up avoiding any covariate shift in the input features. Avoiding any covariate shift in the input features. Okay? What that means is, if the training data is in one scale, the test data is in the other scale, but the data to Y is actually the same. The data to the classifying, the label is, the relation is the same. You can make your learner be a little more robust by essentially upfront changing the input to be scaled such that it's of the zero mean variation. In fact, think about it this way. If I have two midterms, let's say, in one midterm people do very well, in another midterm people do very badly, and then somebody who gets like a 50 points in the second midterm is not equal to somebody who got 50 points in the first midterm, because the first midterm is actually harder. If on the other hand, if you computed their z-scores, it actually allows you to compare. That's what we are doing. Okay? Now, having said this, this part is just pretty much classical statistics does this. The one problem for neural networks is actually this, which is every layer, the first layer of the neural network, the earliest layer of the neural network next to the input side is basically getting the input. The second layer is getting the outputs of the first layer. The third layer is getting the outputs of the second layer. You scaled the input numbers. What happens to the scale of the numbers that are coming in this middle? Do you see what I'm saying? For the fourth layer guy, the input is the third layer activations. And it too can have covariate shift. That means forever, in fact, because of the way the training is being done, right, every weight is changing as you are looking at the examples. From epoch to epoch to epoch, a level 4 layer might start seeing very different scaled distributions of the activations that are coming to it. Do you see what I'm saying? Okay? We need to deal with that. And in fact, for the longest time, people didn't know how to deal with that. And the big thing that changed in 2015 basically is batch norm, which is one of the patented ideas from Google that I'll talk to you a little about, hush tones, so that you won't tell anybody. Okay? But we'll get to that. But there's one more just before that, which is weight initialization. Remember, just like, this is like, when you started the value iteration, you had to put some values and then start iterating. Similarly, when you're doing gradient descent in the weight space, you have to start from somewhere. So you have to put some weights everywhere. So you want to also have some weight initialization method. Once again, the idea for weight initialization is that along with the scaled inputs, the initialized weights should try to keep the threshold units not saturating. Do you understand what I'm saying? Because for every unit, essentially, imagine you are talking about sigmoid units. They look like that, right? And actually, they look better like this. Okay? They look like this. And so only in this region do you have non-zero gradient. Everywhere else you have zero gradient. Do you see this? Okay? So if in fact all the gradients are zero, there is nothing being propagated. The theory is correct, but there is nothing being propagated. It's exactly like, how many of you have done any electrical engineering courses, know something about op-amps? The way, have you ever gone to, my God, have you ever gone to any function where the audio starts going in the middle? And the people say, like this, and then they'll start trying to tune stuff. What is happening there is essentially the amplifier is able to amplify only if the signal is in the working region. And it amplifies by multiplying the signal by a nice value k. So that's how it amplifies. If it is outside of the working region, it essentially sort of squishes the entire signal, because all of them are being amplified. All of them are being essentially floored or ceilinged to a particular level, which is that crazy sound you hear. So much of electrical engineering, much of good circuit design is to make sure that you stay in the operating regions of the amplifiers. Which is why there is something called sound engineering still left. Because if you try to do this, basically you'll be only hearing noise all the time. And that's what was happening in the neural networks if you do not carefully initialize the weights and the input and scale the inputs. You see what I'm saying? In the beginning, people realized this was happening, but there wasn't that much of a real understanding. So let me see what happened. Okay. So for the weight initialization, the idea is very simple. All you're going to do is you basically pick weights to be in, from a normal distribution, that is zero-centered, zero mean normal distribution. The only question is, what about the variance? And the variance it turns out people used to set it also to be the unit variance. Just that's like the most obvious thing to try. Okay, but people have found by engineering, and then they kind of gave some reasonable reasons, explanations as to why this works. But one of the ideas that you can do is if your weight is going along with other weights, n of the other weights to this particular node, that means this node has an input fan-in factor of n, then for these weights, you initialize these weights with 0 mean and 1 by n variance. That's the general idea. There are many variations. In fact, this one is called the Xavier initialization, and that actually works for the sigmoid units. And then there is this ReLU units. Remember we talked about ReLU units too, which look more like this. And there is a slightly different way of initializing, but again, a static initialization of the weights, which makes better sense. And that one is actually called a K initialization. Suffice it to say that basically you're trying to kind of standardize the mean and the variance. The mean will always be 0. The variance, rather than always being unit, it's being made proportional to the fan-in or fan-out or combinations. That's the weight initialization aspect. That finally gets us to this internal covariate shift, which was the last thing that basically got figured out in around 2015, and it's a huge improvement in multiple ways. And here is actually how it looks. And the reason this was written up in hand is I was going to teach these 3 classes back, and as I was just running to the class, I quickly wrote it down, and I never changed it. But then we finally came to it 3 classes later. But it's basically the idea. First idea would be that, as I said, what we're talking about is we need to, just as we scaled the inputs at the input layer, you need to scale the inputs for the internal layers. Inputs for the internal layers are the activations of the layer before it. That means weighted sum, thresholded by the G, whatever is the number. That's what is the activation. Do people understand this? Right? So you'll get a bunch of numbers there. Now, of course, these numbers keep changing as the weights change during the gradient descent. So what was happening is that the internal layers were essentially going after a moving distribution of inputs. The original input layer is just the single distribution, because that was the training data distribution. But the input layers, the intermediate layers, their inputs are coming from other intermediate layers of the network, the one prior to them. And those guys' outputs depend, of course, on the weights connected to them, and the threshold function parameters, as well as the inputs to those weights, and so on and so forth. It's a mess trying to make everybody behave just so that every